Multivariable Calculus, Section 13.7, Integration in Cylindrical and Spherical Coordinates. Let's review triple integrals in rectangular coordinates. Here's our triple integral, f of x, y, z, dv. This integrates f over a solid region T. Note, the change in the volume is the change in the three dimensions x, y, and z multiplied together. And so we have a little cube, and in order to integrate at every single x, y, z value, that little cube and its dimensions shrink down to infinitesimal, and delta v changes into dv, and delta x times delta y times delta z changes into dx, dy, dz. Instantaneous change in volume is equal to the instantaneous change in x, y, and z multiplied together. Now let's review the concept of the polar square. Remember that the polar square looks like this pink region. We have various radii in our picture, and we have a change in theta for this particular polar square, the ith polar square. We have a change in the radius, and then the arc length, the outer arc length, is a portion of the circumference, so it's the change in theta divided by the total circle, which is 2 pi radians, times the whole circumference, and then the 2 pi cancels and we get delta theta times r. And so the area then is just delta theta times r times the change in r, the two dimensions multiplied together. So now we're going to look at a cylindrical block and triple integrals in cylindrical coordinates. And so we have a cylindrical block shown there floating above the xy plane, and the top of that cylindrical block is a polar square whose area we computed or reviewed in the last slide. And then the height of that cylindrical block is a change in z. So our volume of that block, which would approximate actual volume, is the change in z times the area of the top polar square. And as we integrate, those actual changes turn into instantaneous changes. Those discrete changes, rather, change into instantaneous changes. And so dv becomes r dz dr d theta. And so here's our integral in rectangular coordinates. And so we have to change x into r cosine theta, y into r sine theta, and then z just stays z, and dv becomes, as we wrote above, r dz dr d theta. Now notice that we don't have t there anymore, we have u, because t is a description of the solid in x, y, and z, and u is not the actual solid region itself, but a description of the limits on z, r, and theta, and so we had to use a different letter for that. Now, if the function of x, y, and z is 1, then as before, the integral will return the volume of the object, the region, T. Notice that we're going to integrate with respect to z first. So that means that your region, your three-dimensional region T, has to be vertically simple for this technique to work. Triple integrals in spherical coordinates. Here is a spherical block, and this picture is taken from your book, and they've labeled all the different dimensions. And so if we multiply these three dimensions together, we get the change in volume is equal to rho squared sine phi delta rho delta phi delta theta. Now here's a picture with a bunch of little blocks, and so as our spherical block shrinks down to instantaneous blocks, our delta v changes into dv, and all the i's disappear, and the deltas change into instantaneous d rho, d phi, and d theta. So here's our triple integral in rectangular coordinates, and we substitute for x, y, and z their respective values in spherical coordinates. And then dv becomes our rho squared sine phi d rho d phi d theta. Well, that's a mouthful. Now, in order for this to work, a row has to pass from the bottom of the solid up through the top of the solid, and we call that centrally simple. So now we'll jump into the problems. Number 2 says, using cylindrical coordinates and a triple integral, find the centroid of the solid of unit density bounded above by z equal 4 and below by z equal r squared. So here's my picture. Z equal 4 is the plane floating above the xy plane, parallel to the xy plane at z equal 4. And then z equal r squared just means that when r is 0, z is 0. When r is 1, z is 1. And when r is 2, z is 4. And then you're done. So we are vertically simple, which means our method can work. And x bar and y bar are pretty obviously 0, are they not? By the obvious theorem. If not, if you don't trust that, you can always work out the integral for those. The mass is the integral of density times the cylindrical dV, which is r dz dr d theta. And as far as our limits of integration, z is going to go from the bottom up to the top. So it's going to go from r squared up to 4. R is going to vary from 0 to 2. And theta is going to go all the way around the circle from 0 to 2 pi. Notice that when we're integrating with z first, we have to hand off to the next variable, which would be r. So our limits of integration for z should be in terms of r. And so the antiderivative of r with respect to z is rz, because r is treated as a constant, and our limits of integration are r squared to 4. And so we get the integral from 0 to 2 pi, the integral from 0 to 2, and then substituting we get 4r minus r cubed, which we then integrate with respect to r and get 2r squared minus 1/4 r to the 4th. And that's evaluated from 0 to 2, which comes out to 4, and then 4 theta from 0 to 2 pi comes out to 8 pi. So our mass, or volume in this case, since it's unit density, our density is just 1. The volume and the mass is the same, 8 pi. And so to compute z bar, we need the reciprocal of the mass, same integral, except this time we integrate the density, which is 1, times z times dv, which is our r dz dr d theta. And the antiderivative of zr with respect to z is going to be 1/2 z squared times r, which we then substitute our 4 and our r squared. Simplify that. I'm skipping some steps in order to fit this all on the slide. And then we integrate that with respect to r. So we get 4r squared minus 1/12 r to the 6th, evaluated from 0 to 2, which comes out to 32/3, and then the antiderivative with respect to theta is 32/3 theta, evaluated from 0 to 2 pi, and when we simplify, we get 8/3. Which means our centroid is right there at 0, 0, 8/3. Number 10. Using cylindrical coordinates and a triple integral, of course, find the volume of the region inside both the sphere x squared plus y squared plus z squared equals 4 and the cylinder x squared plus y squared minus 2x equals 0. So here's a picture from your text. Evidently they thought it would be too hard for me to draw, and I thought so too. Notice that we are vertically simple, that z passes from the bottom part of the bottom of the sphere up to part of the top of the sphere. And if we look at it top down, here's the image on the xy plane. The red circle represents the sphere and the blue circle represents the cylinder. And we notice that the angle, theta, is going to swing from negative pi over 2 up to pi over 2, and r is going to travel out from the origin to the edge of the cylinder. So we'll set up our triple integral first with words and then figure out what those limits have to be. Theta, the last thing we'll integrate with respect to, goes from negative pi over 2 to pi over 2. Now let's take a look at the equation of the cylinder and change to polar form. X squared plus y squared is r squared. X is r cosine theta. And then we divide by r and solve for r. And so now we know that r is going to go from 0 out to the cylinder, whose expression is 2 cosine theta. And if we look at the equation for the sphere and solve for z, z is going to go from the bottom of the sphere, which is the negative square root of 4 minus x squared plus minus y squared, up to the top of the sphere, which is the positive square root. And again, we're not going to be able to use x and y, so we'll substitute r squared for x squared plus y squared. Now, the antiderivative of r with respect to z is just going to be rz, and when we substitute the plus or minus square root of 4 minus r squared, we'll just get 2 of the square root of 4 minus r squared. And so our new integral is going to have 2, and then the r that was already there, and then the square root of 4 minus r squared. This integrand can be integrated with a simple u sub. You could probably do it in your head. I did. And so we get negative 1/3 the quantity 4 minus r squared to the 3/2, and that's evaluated from 0 to 2 cosine theta. Now I've run out of room on this slide, so I'm going to recopy this last step on the next slide. And so substituting 2 cosine theta and 0, we get this expression for the integrand. And you could factor out a 4, out of the 3/2, and that would make it, let's see, 2 cubed and 8 on the outside. And then 1 minus cosine squared would be sine squared. You could simplify that to sine cubed, etc., etc., etc. Do it by hand if you really wanted to and had plenty of time, but instead I just took out the calculator to do that last integral. And so I get 9.644. Now notice, because of the symmetry here, we could have changed our original problem and gone from 0 to pi over 2 and from 0 to the square root of 4 minus r squared, and then just doubled for each of those changes. So it could have been 4 times that integral. And then your substitution after you integrate would have been a lot easier. Number 24, using spherical coordinates and a triple integral, of course, show that the centroid of a homogeneous solid right circular cone lies on the conic axis 3/4 of the way from its vertex to its base. Homogeneous means the density is the same throughout, so we'll just use 1 for the density, and therefore the volume and the mass are going to be the same. Now here's a picture of a right circular cone. And if you make it any dimensional cone, tall, skinny, short, fat, then you have to introduce some letters and find an equation for the line along the side of the cone, and it gets rather messy. So to keep it simple, I'm going to let R be 1 and Z be 1. And so I'm doing a simpler problem, but if you did the more general problem, it would be the same steps. It would just be messier. So we're going to do a simpler problem here. Now the mass is equal to the volume, and the volume of a cone is 1/3 pi r squared. In this case, r is 1, so we get pi over 3 for the mass. And again, by the obvious theorem, x bar and y bar are 0, and z bar is the reciprocal of the mass times the triple integral of z times the density, which we're just using 1, and then dv is your rho squared sine phi d rho d phi d theta. Now z equal 1 is the plane that cuts off the top of the cone. We need to get that in terms of spherical coordinates. So z is equal to rho cosine phi, and so if we solve for rho is secant phi, and that's what we're going to integrate with respect to first, is rho. So we need to change z equal 1 into secant phi. I just wrote z equal 1 there to represent the plane. We also have to replace the z in the integrand with rho cosine phi. And so now we're ready to integrate with respect to rho. Cosine phi and sine phi are treated as constants, and we get 1/4 rho to the 4th. And that has to be evaluated from 0 to secant phi. Now I took the 1/4 to the outside, and then I canceled a secant with a cosine, which gives us 3/4 pi times our integral, secant cubed, because one of them canceled, and the sine phi is still there. Now you could use your trigonometric prowess to integrate that by hand, but I wimped out and used the calculator since the limits of integration were numeric, and got 1/2, which I then integrated with respect to theta, and we get 1/2 theta evaluated from 0 to 2 pi, and when you simplify that, you do get the 3/4 that we were asked to get. So now I leave you wandering about inside a Menger sponge. Enjoy the problems for 13.7.